I think that we can start. So today we have the pleasure to have with us here Francesca Calore. Francesca is a colleague at CNRS. She works as a chargée de recherche in la PTH in Annecy. Francesca studied in Turin in Italy, and then also she did a PhD between University of Turin and University of Hamburg in Germany. Then she held a postdoctoral position at the Center of Excellence for Gravitation and Astroparticle Physics, known as GRAPPA, in Amsterdam, in the Netherlands. And then she was appointed at CNRS in Section 02 in 2016. So Francesca has quite a broad range of expertise. Her research is at the interface between high-energy particle physics and high-energy astrophysics, and focuses in particular on dark matter phenomenology and indirect searches for dark matter. More in detail, Francesca worked on the characterization and interpretation of the galactic center GVXS, measured by the Fermi telescope. Then she studied the composition of the diffuse gamma ray background, looking at the different components and the classes of sources that contribute to it. She worked on the scrutiny of particle and non-particle dark matter candidates with astroparticle experiments. And more recently, she got interested in exporting techniques traditionally used in data analysis in the gamma ray domain to gravitational wave physics. So during her career, Francesca has been a recipient of several prizes and a lot of recognition. Only in 2021, she received the Médaille de Bronze of CNRS and also the Early Career Scientist Award from the International Union of Pure and Applied Physics. And I read from her outstanding contributions to the phenomenology of dark matter searches that highlight its connection with diverse messengers. So it's a real pleasure today to have Francesca with us. Thanks for accepting our invitation. And now the floor is yours.
Thank you. Thank you, Julia, for the nice introduction. Thanks for the invitation. It's really a pleasure to be here and to give you this overview about how we look for dark matter from the sky, mostly. I'd like to present what is the current status and what are the prospects that we have in the future. So this is broadly the outline of my talk. I would like to drive you among different kind of topics. First of all, to set everyone on the same page on what cosmic probes for dark matter tell us about its nature, and then try to motivate why, from a theory point of view, we look for a kind of specific candidate and how lately the landscape for dark matter models has extended. And in the third part, I'll give you my approach to this kind of challenge, which is the indirect detection approach and how we can really focus on astroparticle observables in order to tackle the mystery of dark matter. So let's start to the evidence for dark matter. So there is mounting evidence for dark matter from kiloparsec-sized galaxies up to the large cosmological backgrounds that suggest that most of the matter in our universe is pressureless and non-baryonic in nature. However, what we really do not know is what is the fundamental nature of this elusive matter component besides the gravitational interaction that we can measure. So here I present a list of open questions in the dark matter cast that has been brought up by different exercises of the community, specifically the SNOWMAS exercise and the UCAPT white paper, where we try to identify what are the current challenges in this search. So first of all, we don't really know how cold dark matter is, and if we have to go beyond the approximation that it is a collisional fluid in the way in which it acts to the formation of large-scale structure. How dark matter is produced in the early universe is also unclear, and this connects fundamentally to what the nature of dark matter is. Is this a fundamental particle or not? This is still open for debate. And then in case we believe in the particle paradigm, does it have a behavior more like a wave or more like particles? And what are the fundamental interactions that this new particle beyond the standard model would have with other known components of our framework? All in all, from cosmic observations, we can infer some properties of dark matter. And in particular, if we have this dominant component of the matter in the universe, this has to be produced sufficiently non-relativistically during the early phase of the universe, so to be cold. It has to be stable enough to be present today. And it does not have any strong granularity at galactic level. If it is a particle, then it should be confined in astrophysical objects that we do see, like dwarf galaxies, and so it should be sufficiently massive to be confined therein. It also has very weak interaction with the electromagnetism, so it's basically dissipationless, and is not very collisional. This information we can derive from cosmological and astrophysical observation of different objects. So all in all, the dark matter evidence requires new physics beyond standard theories. So in the minimal scenario that you can derive from cosmological and astrophysical observation, you have this standard law of a stable, non-relativistic, collisionless dark matter. So what does it mean in terms of mass, spin, it is a particle or not, is actually very, very not so constrained. So what can really break the dark matter, this standard dark matter paradigm, is how dark matter distributes at the smaller scales. And this is where cosmic probe can still have a huge role to play with upcoming surveys, because we can still learn a lot about how dark matter, the large scale structure, distribute in galaxies. So by looking, for example, at distribution of galaxies around halos, we can learn about the dark matter properties more and more. So for example, depending on the number of small scale galaxies, we can learn if dark matter was warmer than the standard cold dark matter paradigm, how much does interact with itself, so it has some degrees of self-interactions. And moreover, by having access to the matter power spectrum at the smallest scales, we can also try to disentangle different models for particle and non-particle dark matter. The challenge here is how really to discriminate between effects that are purely due to dark matter physics and microphysics from effects that are instead induced by baryonic and normal stars and gas in the galaxies. So there is a huge theoretical and numerical development that is ongoing in order to tackle this challenge and be ready from the next cosmic survey. So this is what we can learn from cosmological and astrophysical observation, and more will be done in the future. This leads us to a very broad landscape from a theory perspective. So how we do define good dark matter candidates and what are the current challenges? So let's start from a more production perspective. So how does dark matter, how is dark matter produced in the early phase of the universe? There are two main plausible scenarios that have been advocated in the literature. One is the probably most well-known thermal freeze-out. So what happens if you have a particle beyond the standard model that has a mass and very weakly interaction with the standard model, as it should be for dark matter to account for the cosmological observations, then what you can do is to follow the evolution of the distribution of the phase-space density of dark matter in the early universe in the same way as you do for other particles of the standard model. So you do expect that at a certain point in the early phase of the universe, dark matter is in equilibrium through interactions with the standard model with the primordial plasma of particles. And then, because of the fact that the universe is expanding, at a certain point, the interaction rate between dark matter and standard model particle is not any longer sufficient to sustain the production of dark matter in the left direction of this process. And so the abundance of dark matter freezes out and is frozen at a certain values, which is the relic abundance for dark matter. And this is what we can measure, for example, by looking at the energy density, energy matter density of cold dark matter through cosmological surveys. This thermal freeze out is a very natural way to produce relic particles like photons and neutrinos, but also dark matter in the early phase of the universe. And in this case, as I mentioned before, dark matter should be a particle massively enough and weakly interacting with the standard model. Complementary of this, let's say, cosmological motivation, you also have further theoretical motivation that comes from the fact that such a particle would also solve problems open currently in high energy particle physics, and notably the electroweak hierarchy problem. However, this is not the only way to produce new particles in the early universe. Another mechanism that was invoked in the past is the so-called misalignment mechanism. Whenever you have a field that has a given potential in the universe and for which the initial condition is slightly displaced for the maximum the potential, then with the expansion of the universe, it will slowly roll down towards its minimum and dissipate energy while reaching the final bottom of the potential. The dissipation of energy goes through the production of particles, and in particular, this mechanism can produce the so-called axion. And in particular, the axion is like a new particle that has been invoked to explain the absence of CP violation in the strong sector and can be produced through this mechanism. And in some part of the parameter space, axion can indeed be called dark matter particle. So those are the two top candidates that are currently investigated. And now let me present a bit what is the current status of their search. So weakly interacting massive particles from a phenomenological point of view are particles that have a mass between 1 GeV and 100 TeV, which are very weakly coupled with the standard model and with the Z boson and the X in the X sector. The current approach to look for WIMPs is to delve deep into the parameter space. You can do that with different strategies, which are pretty complementary. First, you can look for the fact that those particles would scatter off nucleons in elements in underground detectors, leaving small traces in the recoil of the target material. And so you can look for these kind of events, and by the fact that those large underground detectors for direct dark matter haven't found a signal of this scattering yet, you can set constraints on the scattering cross-section of dark matter with nucleons as a function of the dark matter mass. So here, this black line is the gray line here is the currently excluded limits from 2013, and here the black line is the actual exclusion limits from 2023, and you can see the huge improvement that in 10 years this kind of instrument gave. And here you can see how the currently operating and the next planned instrument for direct detection will further carve down in this parameter space. On a complementary side, you can instead look, and this will mostly be the second part, the third part of the talk, at how dark matter can give you signal in astroparticle experiments. This is the real indirect detection where you constrain the annihilation or cross-section of dark matter, so the fact that two particles, dark matter particles, can come together and lead to final standard model products. And you can constrain this cross-section, which is strongly related to the same cross-section that gives you the freeze-out abundance of dark matter as a function of the mass. This is the current sensitivity here in yellowish, and here you have the further reach for next generation gamma ray instruments. So we are at the edge of really challenging the WIMP paradigm with these current instruments, but there is still some part of the parameter space that remains open. So the QCD axion received a lot of revival interest in the past, let's say 5 to 10 years. It would be a particle whose mass can span from 10 to the 12 electron volt up to, let's say, 10 milli-electron volt, and has a very specific coupling with the photon through this Lagrangian term. And these Lagrangian terms allow for conversion of axions into photons and back in the presence of strong electric and magnetic fields. In order for the QCD axion to be a good cold dark matter candidate, you need the scale of the symmetry breaking that leads to the misalignment mechanism to be of the order of 10 to the 10, 10 to the 13 GeV, which means that the mass of the axion to be a good dark matter candidate is in the range of the milli-electron volt mass. And this is the current landscape of constraining and searching for QCD axion. This is the coupling with the photons as a function of mass. Here on the bottom are the predictions for the axion mass, because you can try to compute what is the expected axion mass by running simulations of the initial early universe and try to derive what could be the axion mass. And here is instead the current experimental landscape. So there is a very diversified program. You can look for axions that are produced in the sun, where you have you expect strong production of axion from the electrostatic potential of the ions therein. These axions can then reach Earth and be converted in large magnetic cavities. And so you expect to see a signature of extra X-rays from the direction of the sun. This is the principle on which our operating helioscopes that currently set the constraints through the CAST experiment at CERN. Then what you can do is that if you believe that in this mass range, axion is indeed the cold dark matter, you expect dark matter to be distributed in a halo of our own Milky Way. So these conversions of axion dark matter particles in the halo can also occur in other types of cavities pointing directly at high density regions of dark matter in the galaxy. And this is the principle of the haloscopes that are setting very strong constraints down to this yellow band, which is just a reference for a well-motivated parameter space for QCD axions. So there are several detection methods that are systematically exploring this top priority candidate for cold dark matter. However, what it has happened in the last few years is that there has been a strong theoretical exploration of what really are the models that are allowed only purely from cosmological and astrophysical observations. And this has gone hand in hand with a huge experimental developments in order to try to provide sensitivity to different models. And so sometimes you perhaps have already heard of the fact that we have many more models for dark matter, and in particular what it has emerged as promising direction are some models where dark matter and standard model are not connected directly through interactions, but whose discussion goes through some messenger. So you introduce a dark sector where dark matter lives, and the standard model sector that are mediated by some new particles, so some messenger particle. When this messenger is a vector, you have models like the models for massive dark photons, and the connection of the standard model in this case is through kinetic mixing with the hypercharged field potential. You can also have other type of messengers like scalar or pseudoscalar particles, and in this case, the mixing goes through the X master. Those particles can be produced thermally, but you have strong constraints, for example, from BBN and the CMB. This is just to give you an idea on how much broader the landscape can be. So this is, again, the current direct detection status. So WIMPs lives in the right part of this plot, while sub-GeV dark matter particle or dark sectors would actually fill in this gap at low masses. And here is where cosmic probes and large-scale structure can really play a game in constraining a part of the parameter space that is very hard to touch with direct detection method. By looking at how in these models the small-scale structure of the halos would be affected by this kind of interaction and light particles. And for direct detection, this is the kind of current challenge, is to push down the threshold for their sensitivity in order to try to cut down to the left onto this plot. And this is very challenging because you have to be sensitive to recoil energies of the order of the microelectron volt. Indirect detection also can have quite an important role in opening up the probes for these sub-GeV dark matter particles, and a great input is offered by the diffuse emission from our known Milky Way at MeV energies, and I will discuss more about that and how we really need to overcome the current MeV sensitivity gap in measurements in order to be able to further probe sub-GeV dark matter particles. Also, from the point of view of the QCD axion, you can extend the theory and you can have other particles that are very similar to the axion in terms of how they connect to the standard model. So they have a very similar coupling with the photons more specifically. And those axion-like particles are very common in extension of the standard model, like some string theory models, where you always have this spontaneous breaking of global symmetry, as it is the case of the QCD axion. In this case, however, you lose the connection between the mass and the scale of the symmetry, so you open up, if you want, the parameter space. While QCD axion can only live in this band, axion-like particle can actually inhabit the more part of this parameter space, and this is where astrophysics can play a role. And indeed, this is a sketch of the current status of axion-like particles, where you exploit, again, this fundamental coupling between the photons and the axion, which allows, as I mentioned before, to have conversion in the presence of a magnetic field of a photon into an axion, but likewise of an axion into a photon. And you can also have a decay of an axion into two photons. So by exploiting these processes and looking at different astrophysical systems, you can set constraints in this parameter space. And those are the dark matter the axion dark matter detection limits that I shown you before. There is a third, another way to have dark matter candidates, which does not involve any particles. There is a well-motivated solution to the dark matter problem through primordial black holes. So primordial black holes would have formed through the collapse of large over-densities that are born during the inflation period. And whenever those over-densities cross the Hubble horizon, then they can collapse. And those primordial black holes would live till today if their mass is not decreased during the early phase of the universe by Hawking radiation. So through Hawking radiation, that is the emission of charged particles and photons by the black hole itself, the lifetime of a black hole, of primordial black hole, is directly related to the mass. So the lower is the mass, the shorter lived is the black hole, so that in order to be good dark matter candidates, and so to be present still today and account for the cosmological cold dark matter density, they have to have masses larger than about 10 to the 14 grams. So those primordial black holes behave as cold dark matter on cosmological scales, but they would present granularity on galactic scales. And there is a broad program in order to try to constrain what is the fraction of black hole that could account for the total cold dark matter density. And you will see often this plot where you have this fraction as a function of the primordial black hole mass. The fraction is bounded from above to be 1 if the primordial black holes can account for the totality of the dark matter density in the universe, and can be constrained through different observations. At the high-end mass, one very strong constraint is given by the fact that those primordial black holes would accrete gas as normal black holes like astrophysical black holes do, and by the fact that you haven't seen any X-ray or radio signatures around these putative dark matter candidates, can set strong bounds, as well as gravitational wave emission that you could have when two primordial black holes form binaries and can leave an imprint in the gravitational wave coalescence binary events. The strongest constraints come from microlensing, where you have a black hole passing through the line of sight of a star, which is surveyed with this kind of optical instruments. And if you see a temporary magnification of the starlight when the black hole crosses the line of sight, then you can have a microlensing event. By the fact that there is absence of these microlensing events that could be due to primordial black holes, you can set strong limits on the fraction of primordial black holes dark matter. And on the lower mass end of these candidates, you can constrain the black holes by the fact that if they are there today, they would emit charged particles and gamma rays, so they would contribute to the diffuse gamma ray emission and to the flux of charged cosmic rays as we measure them with cosmic ray observatories and gamma ray satellites. So those are the evaporation bounds. As you can see, there is a window here between 10 to the 18 and 10 to the 21 grams in mass that is currently not covered by any constraint. So there is no current robust observational constraint in this mass range, and this is the so-called asteroid mass gap, and this is a very interesting range where to look for primordial black hole, because it's the only one for which black holes could be good dark matter candidate. So all in all, the landscape for dark matter is very diverse, as I hope I have conveyed you. And the phenomenology of all these candidates is very different. So then how we really do look for them and how we can break up this parameter space in an effective way. So what you can do and what people have done is to have a mass dependent approach. So let's consider candidate, classify them in ultralight, light, heavy, and ultra heavy candidate, and organize them this way and look for phenomenological signatures. The other way that you can tackle the problem with is to organize the searches based on observables. So what are the relevant astroparticle observables that you can identify, and how you can classify candidates based on their specific signatures. So this would be the focus of my talk, the rest of the second part of my talk, where I want to give an example of how we can use astroparticle observables that are very different in order to probe a huge range of dark matter candidates. And in particular, because of sake of time, I will focus on a specific example, which is how we can use the gamma ray galactic diffuse emission from MEV to PV energies in order to probe different candidates. So then a bit of astropart. So we have measurements of the diffuse glow of our own galaxy at different energies, from the measurements at 100 keV from the spectrometer aboard the integral up to basically sub-GeV energies with the gamma ray LASO. The emission from our own Milky Way at low energy is supposed to be purely diffuse and to be dominated by the photons that comes from cosmic ray collisions with the surrounding medium, so gas and the radiation. While at higher energies, we do expect a sky which is dominated instead by individual, very high energy gamma ray sources. And nonetheless, what we measure also at sub-PV energies is a relic of a truly diffuse emission, which might be either made of sources that are too faint to be detected with this technology, or come from cosmic ray collisions. All in all, we can use this multi-wavelength information in order to understand what kind of leverage we have on dark matter physics. So how do we do that? In order to look for a signal of dark matter in astrophysical observation of the gamma ray radiation, the observables that we are given with is the flux of photons in a given direction of the sky per unit energy. And this is composed by partly by an purely astrophysical signal, which is either from these cosmic ray collisions or from point sources. And on top of that, we look for tiny signatures that would come from dark matter processes. So the challenge for this type of search is, of course, to have control on the diffuse cosmic ray processes and the point source populations that are in our own galaxy. And this, of course, is per se a big topic of research. And in order to be able to push the sensitivity on a dark matter signal, one has to be aware of uncertainties, convolve them properly in any analysis, and exploit the multi-messenger and multi-wavelength connection. So let's start from soft gamma rays. So the diffuse emission from our own Milky Way has been measured since COMTEL towards more specifically the center and the disk of our own galaxy. And Integral also has measured this emission along the galactic plane. And more recently, we have pushed the sensitivity to Integral up to 8 MeV by providing the measurement of the diffuse emission at these high energies. And what you can do once you have this diffuse emission measurement is to use it in order to understand what are the conditions of transport at these energies, but also for constraining particle and non-particle dark matter candidates. So let's see how you do that. So first of all, you need to have a model for the astrophysical contributions that you think are giving basically most of your MEV emission. And the MEV emission, diffuse emission, is dominated by photons that come from inverse Compton scattering. Inverse Compton is a process for which cosmic ray electrons that are accelerated and injected into the interstellar medium by cosmic ray sources like supernova remnants upscatter low energy ambient photons like the one of the CMB to MEV energies. The outgoing energy of the photon strongly is linked to the energy of the field radiation and to the energy of the incoming cosmic rays. So that for GeV electrons, you have outgoing MEV to GeV photons. The inverse Compton is the dominant component of the MEV sky. And on top of that, you have to account for other contributions, like from the fact that integral is not very good in resolving point sources. So you would have a glow of diffuse radiation from sources that you don't see individually, but still give you a diffuse gamma ray emission. And then at these energies, you have nuclear lines that you know how to model, including the line that would come from electron-positron annihilation at rest, giving you the 511 keV line. So this is your astrophysical model. And on top of that, you add a contribution from dark matter. From the theory of dark matter, in this case, you have this equation. Again, this is your observable, and you link it to the distribution of dark matter in the galaxy and the number of photons that you produce in the process that you are considering. In this case, either decay or annihilation if you are looking at particle dark matter, but you can also have photons from Hawking radiation if you're looking to primordial black holes. And this term here is an overall normalization that contains the particle nor particle physics parameters, like, for example, the decay rate or the annihilation cross-section. So what you do is that you add your model component in your fit of the diffuse emission sky, and you want to test if your data do prefer this additional component, or rather your null hypothesis where this additional component is not present. So by fully including the dark matter contribution in the SPI analysis pipeline, we actually concluded that no signal is detected. And let me just point out that this was the first time that the dark matter signal was properly included in the analysis and extraction of the SPI flux measurement. So what you can do when you have no signal that is detected is to set upper limits on the dark matter flux. And from these upper limits on the dark matter flux, you can then derive what are the upper limits on my particle or non-particle physics parameter. So basically, just with one data analysis, you can then recast in different parameter space for different dark matter candidates. So you can constrain, this is what we have done with on the fraction of primordial black hole as a function of the primordial black hole mass, giving the strongest constraints today and carving a bit more into the parameter space. And same is for light decaying particles, like axion light particles, showing that this data can still be very impressive and giving strong constraints on the dark matter hypothesis. And this motivates even further the need of future missions that would cover the current gap in sensitivity at these energies. So let's, in the last 10 minutes of the talk, let's then move on higher energies and more specifically to the GeV sky. So since 2008, the Large Area Telescope aboard the Fermi satellite is taking impressive data of the diffuse glow of our own Milky Way, which is here in red, where you can see that is the structure of the gas. This is really the diffuse emission that comes from the collision of gas, of cosmic rays with the gas, but also measure the sky at higher latitude. This is an all-sky survey where you see here you have a very good definition of individual point sources that are astrophysical objects like active galactic nuclei, blazars, and star-forming galaxies that do emit gamma rays and would appear as individual point sources in the Fermi-Lat sky. And one interesting and very challenging topic that has come out from LAT analysis was the discovery of an excess of photons towards the galactic center, which could not and cannot currently be explained by standard mechanism for gamma ray production from, for example, the galactic diffuse emission. So this galactic center excess is well established and is there since more than 15 years now. But the origin of this excess is really unknown. So one of the very first interpretations that were put out is that this excess can be due to dark matter annihilating into the Milky Way and leading to final photons. So really a very standard WIMP particle that for which you would predict a signal like the violet one here. And here are the data of the galactic center excess. And most strikingly, the shape of the excess in space really does match standard expectation from dark matter models. On the other hand, there were many other hypotheses that were put forward, and in particular, the fact that you can have a large population of astrophysical objects, astrophysical gamma ray emitters, that towards the galactic center are very difficult to identify as single sources, and therefore would emit, again, as in the case of the MEV emission, a glow of photons. So these unresolved point sources are a promising explanation for the galactic center excess, and in particular, the sources that do match the spectral energy distribution of the excess are the pulsars and millisecond pulsars that are detected as gamma ray emitters by the LAT, and that we will need to have a very large population of these compact objects towards the galactic center in order to explain this kind of anomaly. So from the point of view of gamma rays, a lot was done, and I also played a role there in order to understand what is the ultimate reach of current observations in order to probe the origin of this excess. So besides this diffuse large-scale emission, what you can try to do is to disentangle these two hypotheses by looking at the statistics of photon counts. So if the excess is due to something that is smoothly distributed in space, then you would have a thoroughly diffuse emission, and the distribution of photons of number counts per pixel would have a given distribution. Instead, if you have something that is more clumpy on small scales, like a population of point sources, the distribution of the one-point correlation function of photons would change. And based on this statistical approach, people have shown that there is evidence for at least a fraction of the excess to be due to unresolved point sources. And on top of that, if you look at the large-scale distribution of the photons, it seems that the photons do prefer something for the galactic center excess to be distributed more like old stars in the galactic bulge, rather than a purely spherically symmetric dark matter profile. So all in all, there is a strong corroborating evidence for the fact that at least partially the galactic center excess should be of stellar origin. However, inferring the properties of the diffuse emission and the point source population at the same time, it's very challenging with current methodologies. So what is the way forward? At least if we just think about the point source origin of this excess, one possible solution is to go multi-wave. So if really this excess is due to pulsars and millisecond pulsars, then we know that those are astrophysical objects that do emit in other wavelengths. We see them in radio and X-rays, and indeed we do primarily detect them at radio frequency thanks to the very regular beam radiation. So Also in X-rays, if you just take the hypothesis of the galactic center excess to be due to millisecond pulsars, and you made a phenomenological model of these pulsars and X-rays by using multi-wavelength information, then what we actually found is that the possibilities that you have a large population of pulsars in the galactic center is not currently excluded by Chandra and XMM data. And more than that, we could also identify through multi-wavelength matching a sample of hundreds of promising candidates that could be follow-up. And this is a current a huge effort of what I'm doing, and does have little to do with dark matter, which is trying to find those compact objects with a radio of follow-up timing campaign in order to be able to find evidence for these very far pulsars towards the galactic center. There are finally also other complementary approaches which try to tackle the origin of the excess from another point of view, which is, okay, let's suppose that my excess is due to dark matter, then those would be the best fit contours in cross-section and mass, thanks to which I can explain the dark matter hypothesis. But again, dark matter models would predict multi-wavelength correlated signal, and so I can try to check other observables and see how this can constrain the interpretation of the galactic center excess in terms of dark matter. So this is what is done. This is just a summary of the current search for WIMPs with indirect detection, a bit more detailed of the one that we have seen in the very early slides. Where you see that in this parameter space of annihilation cross-section versus mass, you can have different type of observables and searches that can tackle the GVXS interpretation blob. So all of these will deserve a dedicated, more detailed explanation, but bottom line is that you can use cosmic ray observations, for example, of antiproton, or radio emission from other galaxies like the Large Magellanic Cloud in order to set constraints in this very same parameter space. And this is based on the same dark matter model because, again, you would predict multiple signals from the same model that also can explain the galactic center excess. Before concluding, I also would like to give you an overview on the latest measurements that have been done at the sub-PV by Tibet AS Gamma and LASO. So they have measured diffuse emission from the galactic disk. This is just the first measurement from Tibet AS Gamma, but more recently we had the measurements from the LASO array. This is mostly due to unresolved endpoint sources, but the nature is not fully understood yet. However, also at this very high energy, you can have a leverage on looking for dark matter signal. This won't be WIMP any longer. This should be high and heavier dark matter candidates, which could come from the decay, for example, of an inflaton field. But all in all, you have some strong potential in these observations. And more especially, you can exploit the angular distribution of the arrival direction of the photons, and the same way you do gamma ray energies. And so this is just an opening on this new frontier. And more recently, there was a paper from the LASO collaboration, which used those observations in order to set a constraint on the heavy dark matter decay as a function of dark matter mass. You see, we are at 10 to the 7, 10 to the 8 GeV, so much heavier masses than what I told you before, where the LASO observation can really have a breaking through role in giving you constraints on these particle candidates. So then I would like to go to my conclusions. So I hope I gave you an overview of why First of all, we have evidence of dark matter, what we can learn based on cosmic and astrophysical probes, and why we talk about dark sector, why we talk about QCD actions, why we talk about WIMPs. But more importantly, I hope I conveyed the message that astroparticle observables offers you a way to really have a very diverse and interesting approach to the search of dark matter. And with future observation and exploited the multi-wavelength paradigm, we can really try to access portion of the parameter space that are so far uncharted and hopefully offer new windows for detection. So I thank you for your attention. I'm happy to take your questions.
Thanks a lot, Francesca, for this nice overview. We have a question.
Thank you, Francesca, for this very thorough description of the dark matter searches. So my question is, we should look for the dark matter where there's no other matter, okay, to avoid confusion with pulsars or other things like cosmic ray scattering. So we should look far out of the Milky Way, and we should look in dwarf spheroidals. And I know this has been done. So for example, Fermilab has detected this big haze that goes very, very far out, at least on the sky, okay, far out of the galactic plane. So I was wondering what you can tell us about that, and can you confirm that when you combine all the dwarf spheroidals together, you sum up the data, there's no excess gamma ray emission that would be polluted by, that would be caused by astrophysical sources other than dark matter?
Yeah, absolutely. So you're right. First thing to do is to go in a clean environment, which is either to go high latitude, where you only have point sources and the diffuse extragalactic background, or to go to dwarfs. So here is just in this summary plot, you have the current limits from dwarfs, which are this pink line here and this orange line. So we have stacked, I mean, people do stack all the dwarfs together. There is no excess at all coming from any of them. And yet the constraints that you can set on this parameter space are not so strong, in a sense that still the dark matter abundance in dwarf spheroidal galaxies is nothing compared to what you expect towards the center of the galaxy. And on top of that, whilst dwarf spheroidal galaxies were thought to be a very robust probe for dark matter, because we thought, okay, we know well the dark matter distribution. However, you realize that in order to set stronger and stronger constraints, you need to include ultra faint dwarf spheroidal galaxies, for which you only have very few stars. And so the uncertainties also from this probe, as it is from many others, is huge because of the fact that still you have high uncertainties in the determination of how much dark matter there is in galaxies that do only have tens of stars.
Other questions?
Thank you for the very interesting talk. Maybe I missed this, but can you comment a bit about modified gravity candidates for dark matter, whether any of the presented cosmic probes can actually help in distinguishing them from other candidates?
Okay, so I'm not an expert on modified gravity dark matter scenarios. What I know, and correct me if I'm wrong, is that indeed, currently, we don't have like a theory of modified gravity that can account for these very different scales of evidence from galaxy size up to the CMB, basically. So that's my knowledge in a sense that as long as we don't have anything that can link the different scales as a particle or a particle dark matter solution can do, is then very hard to use indirect detection, of course. And for for future cosmic probes, since my current knowledge is that there is nothing that can satisfactorily satisfy the CMB without introducing an additional degree of freedom, which is in the end a light particles, then I don't know what else it can be done in the direction, but it might just my ignorance on that. Sorry.
Thank you very much. Very nice talk. And my question is, could you tell us more about this project that you have to observe the central part of the galaxy with radio telescopes?
Yes.
Is the intent to resolve these pulsars or?
Yes. So the idea is that, so typically pulsars are identified with radio waves, as I told you before. And the main issues so far to discovering pulsars towards, let's say, in the inner few degrees around the galactic center, and especially millisecond pulsars, which are much fainter, is because when is emitted, the radio wave has to travel through the interstellar medium, and in particular, the waves are broadened by also loose coherence because of multiple scattering with free electrons. So this is a problem of scattering and dispersion of the pulse. And so in order to see those objects, you really need very deep observations, which means that perhaps on one target, you have to put 10 hours of observations. So the surveys that have been done so far in radio astronomy were rather interested in shallow surveys of the galactic disk, the galactic high latitude regions. And so they were not sensitive at this population. But of course, there is a strong interest also for the radio astronomy community to find millisecond pulsars towards the galactic center. And so now, also motivated by this galactic center access, we have a program to really have like 10 hours observations of some of our X-ray targets. Also, the data analysis is then challenging because if you want to look for accelerated binary objects, it's not so easy with very long integration times. But the hope is to at least find some counterpart in radio of our own X-ray candidates. There are a few promising candidates, but they need radio follow-up to be confirmed.
Thank you.
Well, we have time for a last question. Well, if there isn't any question, I have a very naive one. So you talked about this pulsar, the possibility that this excess is due to pulsars. Are other non-dark matter candidates that could explain this excess?
No. So if you have dark matter, this should be a particle dark matter in order to produce photons through standard dark matter, standard model interactions. PBH cannot do the game, because they would be, you cannot have stable PBH today and give you GV radiation, so they would be already gone by now. So.
And there isn't any other astrophysical source that can...
No, okay, yes. So dark matter candidate, no, but other astrophysical interpretation. Okay, yeah. Sorry, I misunderstood. No. Yes, sure. So there were other astrophysical interpretation that were put forward. The easiest scenario you can think of is that you have extra injection of cosmic rays at the galactic center. So you can have either extra injection of protons or extra injection of leptons, which could come from, for example, an enhanced star forming activity of the central molecular zone in the now or in the past. Or you can also have, and this is shown to be working, a burst activity of the central massive black holes. So we have signs like the Fermi bubbles that, of course, the history of the galactic center is alive and active. And so it might be that some bursts, like the ones that cause the Fermi bubbles, might also have been in place in giving you this extra burst. For the extra burst, you need, however, leptons, because if you have protons, the morphology, so the spatial distribution of the photons that comes from proton gas interactions would be more like gas structured, and so this does not match the galactic center observations. So you would substantially need extra injection of leptons.
Okay.
And this is the other promising thing on which you have a very little constraint, though, observationally speaking.
So it is very well constrained.
And this, no, it's not very well constrained. Okay. But then what is hard is to understand if this small scale power that there is in gamma rays is due to clumpiness in the gas or really real point sources. So this is still something that you cannot exclude 100% because you don't have a mapping of the gas on those in yet large size region at this precision. So you don't know, is there like...
so it's a matter of resolution of the...
It's a matter of resolution of the gas maps.
Okay.
Yeah.
Do you think Athena X-ray telescope can play a role there?
For
the structure of the diffuse X-ray gas in the center?
So yes, in a sense that, and this was something that we briefly started to look at already. I mean, there is the detection of these chimneys, right, at the low base of the Fermi bubbles with current telescopes. And there might be a gamma ray connection, and this was also invoked. I'm not the first one telling that. This brings up another huge problem, which is what is the degeneracy between the galactic center excess, whatever it is, and the Fermi bubbles. And till we will not have a model for the Fermi bubbles, so from the point of view of the gamma ray analysis, the Fermi bubbles are phenomenologically defined as a component having an hard spectrum in energy. So then you can disentangle something that is not so hard in energy distribution from something that is bumped to a 2 GeV. So you can say those are two distinct components. But we don't have, since we don't have a model for the Fermi bubbles, it remains a fundamental degeneracy between these two components. So perhaps having, I mean, I think in this direction, a mapping of the diffuse X-ray emission, and then if we can understand better where this diffuse X-ray emission comes from, is it really from an active history of the galactic center? Can we have a more informed multi-wavelength model to forward in gamma ray analysis? Then it can help breaking the degeneracies. But it's really a multi-wavelength game. So the more you learn about the galactic center, the more you can inform your gamma ray analysis with informed physical priors on the components.
What about CTA? It has resolution in the gamma rays.
Yes, so CTA has been is definitely the next frontier for more specifically if you're interested in the galactic center excess. So this excess is peaked at a few GeV. It has an high energy tail. Spoiler alert for hopefully a paper which will be out in 2 weeks. And the question is, if the excess is due to point sources, can they emit, but this was also discussed in the literature, they could have an high energy tail due to inverse Compton scattering. So if you have pulsars, they do emit electron, they would do inverse Compton on the interstellar radiation field in the galactic center, and they can lead a signal to CTA. So definitely, if you see an excess which is compatible with inverse Compton from a population of sources, this could gives you some interesting light on the origin of the excess. But does it mean that you don't have dark matter at the TV scale if you find an excess in CTA? Yep. So you are back to square one, but with much higher angular resolution. So perhaps you can really truly try to disentangle diffuse emission from a point like source one.
Okay, so I'm afraid we need to close it here. So thanks again, Francesca.